In this video, I'm going to show you how to define the transfer function in a different way. We know how to define transfer function by define the variable s. Then we can write the system down. Then there's another way by using numerator and a denominator. The numerator is a polynomial. It's the pendulum example. The numerator is a constant. It's 1 over m times l squared. Then the denominator is s squared plus g over l. Then it is a polynomial of order 2. So the coefficient for s squared is 1. Then there's no s term, so the coefficient is 0. Then for the constant term, the coefficient is g over l. Then we define the system, we call it TF, is short for transfer function. Then we have the numerator and denominator. Then we define the system. Then we can also define the time. The time, the starting time, the final time, the resolution. This would mean we want to know the time for every 0.02 seconds. Then we can call step, have the system defined here, and the time defined here. Then you can get the output. You can plot the output versus t, the time. Then we times r to d, that's readings to degree. Then we can use x label, time, y label, pendulum angle. It's degree, not reading. If you use standard unit, the output of the unit of y will be reading. It's common to use degree, so we transform it to degree. If you hit run, then you will see the plot. It shows how the angle of the pendulum changes over time for 10 seconds. Here is another MATLAB code to show you how to build the simulation model using Simulink. Here it is to clear some variables, then clear figures. Here sim means Simulink. Simulink name is figure 220AX. This is this one. Then the output will be here is the output. Then have T out. Then again here reading to degrees. The Y output have two outputs. One is for the linear model here, another one for the nonlinear model. Then we can give the title, label, X label, Y label. We can limit the axis, the size of the axis. The time will be from 0 to 10. The degree is from 0 degree to 50 degree. We have the grid on, then hold off, and the two figures will draw in different plots. Then how to see this Simulink model is built. Let me give you some general idea. You see here is step signal, this will be the input. Then here is a constant, is 1, this is the step input. The step input is applied to both the linear model and the nonlinear model, but actually they have the same input. Then here we have this TC, the torque. Torque also applies to the nonlinear model. Then we know this output is sit output state. Then here is integral. So here it should be state first derivative. Then on the other hand, on the other side, it will be state second derivative. But this is a feedback loop. So state is here. It times the gravity constant. Then we know how it works. It's equal. So the TC is positive minus G times feet. So M is 1. In this case, the ball is 1 kilogram. Then we have state second derivative. The same for the nonlinear model, except that we have this sine function. Then we times the gravity constant. Then here we have TC. Then we have minus G sine theta equals to, again here, second derivative, the equation of motions. Then here we hit run. It will generate 2 plots. One is for the linear model. One is for the nonlinear model. You will see when the angle here, it is less than 15 degrees, then the output of the two models are very close. This means the linear model is a good approximation when the angle is small. But here, the torque we applied is 1 Newton torque, 1 Newton meter. Now let's see if we increase the torque, what's going to happen. So we have a different program, exactly the same, but with a different Simulink model. For this Simulink model, exactly the same, but the torque here is 4 Newton. We still have the unit step, but we time the unit step signal by 4. Then let's run this program. Now you see the figure. So the blue one is the linear model, and the red dashed curve, the nonlinear model. You see, in this case, they are quite different. That, in other words, the linear model is not a good approximation for the nonlinear model when the torque is large. Then you see from the angle almost go up to 50 degrees. That to say, when the angle is too large, we cannot use feet to approximate sine feet. In this case, we have to modify the linear model to make it a good approximation for the nonlinear model.